Have you ever been gifted some fresh cut flowers? Or maybe you bought some fresh flowers for your sweetheart. What do you do with them? You probably should put them in water, right? Well, what kind of water? Should you put them in fresh water or maybe some salt water? What is going to be best to keep the flowers alive and looking their best the longest? Well, in this podcast, we're going to take a look at water movement, water regulation, water potential. We'll find out the answer to our flower conundrum. Let's get started. So in the last video, we learned about osmosis. Osmosis is just the simple diffusion of water across a membrane. So there are some specific circumstances for this to take place. Diffusion of water is from a high concentration to a low concentration. Now look that I was really specific. So osmosis is the diffusion of water from a high concentration of water to a low concentration of water. So osmosis, when we think about osmosis or the movement of water across a membrane, we're always talking about whether the water's in high concentration or the water's in low concentration. So take for example here our YouTube again. So we've got some water here, we got some water on this side separated by a selectively or semi-permeable membrane. So water can easily move across this. And right now, they're pretty much equal, right? The concentration of water is equal to the concentration of water there. Well, what if I took some sugar, some glucose there? And I take that and I put it in this particular side. So now, this side has a lot of sugar in it. Well, if you think about it, if the sugar concentration on this side is up, that means the water concentration must now be down. Because there's some sugar in it and they're equal, the concentration of water over here is lower than over here. So the question then becomes, what direction does the water move? If the water can move across this membrane, it will indeed go in this direction. Because there's now sugar over here, so there's a lower concentration of water on this side because it now has sugar in it. So that means the water will move to that side to help equalize that concentration. Okay? So this is osmosis, the diffusion of water from a high concentration of water to a low concentration of water. All right, so when we talk about concentration, we give it some terms and we compare the total concentrations. Here are the terms we give: hypertonic, hypotonic, and isotonic. So let's break these down. Hypertonic, you think hyper, you think extra, more. Hypo, you think below, right? Iso, you think same. So basically, these terms, hypertonic means there's more solute and less water. And when we're talking about solute, we're generally talking about salt or sugar, but it could be lots of different things. So in a hypertonic solution, there's more sugar, less water. A hypotonic solution means less solute when compared to others and more water. This is all about comparison to environment or cells, okay? So we'll use these words when we're comparing, say, a cell to its solution that it's sitting in. Isotonic means equal solute and equal water in this particular circumstance that we're looking at. So let's take a look at some examples here. So in a hypertonic solution, all right, so here's our cell, all right, here's the cell. Inside the cell, over here is outside the cell. So the solution, which is outside the cell that the cell is sitting in this case is hypertonic. Notice that it has more solute than this does in here. And let's just say this is salt. So look at all the salt molecules, salt particles out here. So if the solution is hypertonic, that means there's more solute out here. So the water will move there because inside is the higher concentration of water. So remember, water moves from a high concentration of water to a low concentration of water. Look at isotonic, this solution. You can kind of see, oh, they're about equal. Okay? So there's equal amounts of solute or concentrations of solute on the outside as there is on the inside. Isotonic. All right, well, look at this. In this last example, the solution outside, right? Notice where the label is, we're outside here, is hypertonic. So hypertonic solution is on the outside. So what we see here is that in this case, there is a higher concentration of water on the outside, right? So there's more water concentration here than there is here, so therefore the water is going to move into the cell, okay? So we've got to be really specific when we're using these terms. Don't just throw around the word hypertonic, hypotonic, unless you put another word after it. So you would say hypertonic solution. Or you might say the cell is hypertonic to the solution. Just make sure you're being really specific when you use these terms. So how do we manage this? Well, cell survival depends on balancing this water coming in and out, right? So I'm giving you a few different scenarios here. One, a hypotonic solution, so hypo, think less. And in this case, we're gonna talk about salt. We could be talking about sugar, but I'm just gonna pick salt here. So hypotonic solution, like fresh water, right? Fresh water has a low amount of the solute salt. Isotonic would roughly have a balanced, right, to your cells, balanced solution, little salt, not too much. And then a hypertonic, right, extra more, would be very salty, right, very salty, like salt water. So different cells react differently in different solutions. So let's start with some animal cells, right? Everyone's favorite animal cell, a red blood cell. In an isotonic solution, right, a balanced solution, water will go in, water will go out. That's because the salt concentration outside is roughly similar to the salt concentration inside. So a little water will go, a little water will come, but it's pretty balanced. Now, what if we took a red blood cell and put it in fresh water, right? So what's going to happen in this scenario is that because there's a higher concentration of water outside than inside, right? Hypotonic solution, which means less salt. If there's less salt out here, that means there's more water out here. So that means the water will rush in. Well, what's that going to do to the red blood cell? It will lyse, explode, right? So this is why we would never want to inject pure fresh water into your veins or arteries. We would instead, if you needed, if you were dehydrated and we had to get some water into you, we would use an isotonic solution, like a saline solution, because that is the same level of concentrations as your cells. So then let's say we put that red blood cell in a hypertonic, some really salty water. Well, in that case, what would happen is the concentration of water inside is greater than outside, so the water would leave. The water always moves from high to low concentration. So those are animal cells. Let's take, for example, some plant cells, right? In the animal cells, if it's hypotonic, it will lyse. If it's iso, it'll stay normal. If it's hypertonic solution that it's placed in, then of course it will shrivel as the water leaves. Plant cells are different though. In a balanced, right, a little salt water, right, not too much, not fresh water, but not salt water, what's going to happen is your plant cells will take in some water, will leave some water, but the cell itself will remain kind of what we call flaccid, right? It's not really rigid, which we need our plant cells to be. So if you put your flowers, your fresh cut flowers, in some balanced isotonic water, they're gonna just kind of slowly wilt. Fresh water, however, what will happen is, because there's a high concentration of water outside, the water will move into the cell. Now, remember up here in the red blood cell, that caused it to burst. But here's a big difference. Plant cells, you will remember, have this cell wall that's rigid. So it is less likely to burst. So in fact, what's going to happen is the water will come in and it will create what we call a turgid pressure. So that will keep the cell walls with some pressure pushing against them, right? Because there's water in. That means the cell is plump. It's pushing up against the cell wall. It retains that rigid, turgid shape, okay? So you should put your plants, your fresh cut flowers, in fresh water. What if you put some of those fresh flowers in salt water? Well, what's going to happen is, of course, because there's so much salt out here, which means there's little water, the water will go from a high concentration inside the cell to outside of the cell, and it will what we call plasmolyze, or it will kind of shrink and shrivel, just like the red blood cell did. Okay? So as I mentioned, let's take it back to the very first slide. You should put your fresh cut flowers, most of them anyway, you should put in a fresh water. Just fill it up with fresh tap water. Put your plants in there, and they'll survive a lot longer than if you'd put them in any of these other situations. Okay, so we might have some sort of problems with osmosis to think about. So if we were in the lab and we wanted to emulate a cell, one of the classic experiments is to take a beaker, fill it with some sort of solution of water, and then try to make a cell. Well, if you're going to make a cell, right, it's got to have some inside, but one of the tricky things to come up with is how do we make a cell that's got this semi-permeable membrane around it? Well, a lot of times in the lab we'll use something called dialysis tubing, right? Dialysis tubing they use patients that are on dialysis, and it's got these tiny small little holes in the membrane, right? So water can move back and forth, in and out, in and out. So dialysis tubing makes a good membrane, okay? So basically what we've done here is we've just made a cell, and in the cell it's got dialysis tubing as the membrane, so water can go in and out. And inside the cell, we've got a 0.4 molar sucrose solution and some water. Now, in the environment, the solution around the cell, we've also got some water, but only 0.1 molar sucrose solution. So when you're solving one of these problems, the first question you always want to ask is, well, how big are the holes in this tubing in the membrane? Can sucrose get through? Because if sucrose can get through, then that sucrose might just come out. Dialysis tubing, though, is generally, it has pretty tight or small holes, narrow openings. So in general, we say these sugars probably won't move too much. So in this case, we're going to assume the sugar stays inside and doesn't move across the membrane. So the only thing moving will be the water. So let's predict. What direction is the water going to move? To do that, we need to define the environment and we need to define the cell. So the cell, when compared to the beaker, is that hypertonic or hypotonic? What do you think? Hyper, right? Because if you think about it, the cell has 0.4 molar, while the environment only has 0.1. So in terms of the solute, it has a higher concentration of solute, 0.4. So the cell is hypertonic, which then means the beaker is hypotonic when compared to the cell, okay? Because it has less sugar compared to the cell. So now the question, which way does the water flow, into or out of the cell? What do you think? So the answer is into the cell. Why? Because out here there's less sugar, which means there's a higher concentration of water. So water moves from a high concentration to a low concentration. Water, in this case, will move into the cell. So let's do another problem where we're actually going to calculate this potential of water to move. So in other words, if I keep saying things like, oh, water's going to move in, right? It's got the potential to move into the cell. We can actually calculate that and we call it water potential. So basically, water potential is just the potential for the water to move. What pressure is it going to move in? How much water is going to move into or out of the cell? Okay, so we abbreviate it here with this Greek letter. So water potential is basically the pressure potential plus the solute potential. Let's break those down. Pressure potential would be any pressure that's applied, whether it's direct pressure or it's pressure because of the atmosphere, whatever pressure is being applied to the situation. Most of the time in an open container, there is no pressure potential, right? Because the potential of the atmosphere is pretty low. The solute potential is the potential of the water to move based on the solute. All right, so what solute are we talking about? In this case, let's talk about some sugar. So we're going to take some glucose and we're going to put it in this tube. Well, we already talked about what's going to happen, right? Because now the sugar is here, which means there's a lower concentration of water now over here, a higher over here. The water will move from a high to low concentration. So the water is going to move in this direction. And so in a way, you could say the sugar kind of caused the water to have some potential to move. We call that the solute potential. The potential of the water to move based on the solute that's there. So let's then say we took our perfectly trained hand and we applied some pressure. Well, what's going to happen if we apply some pressure and push water through this membrane? Oh, even more is going to go. So in this case that you see here, you'll notice, well, water was already moving because of the solute. Now we've applied some pressure, so the total water potential is going to be even greater to move because of the pressure plus the solute. And as I mentioned, in an open container, the pressure potential is usually 0. Okay, so this is cute in a nice little laboratory experiment, but what about in the real world? Let's say we have a plant cell sitting in a solution of water. So here is a problem, a practice problem. Let's see if we can work through this. So a turgid plant cell, if you remember that means water's going in. Water's going in, so this must be some sort of fresh water. Water's moving in. Sitting in a beaker and has a solute potential of -3 bars, right? So if we're looking at our solute potential, in this case, it's -3 bars. It has a pressure potential of +2. +2 bars. Why is that? Well, think about this, right? If water's continually moving into this plant cell, the plant cell will essentially, that water will be pushing against the cell wall, creating some pressure to keep it rigid and turgid. So basically, the plant cell with the cell wall will start to show pressure against the outside of the cell. All right, so that's where we're getting this +2 bars. But at the same time, the solute potential is bringing some in, right? So you've got water pushing out against the cell wall, but you've got some solute, some salt, some sugar or something that's bringing in water. So we really kind of have to figure out and calculate what that is. So how do we calculate this? Let's do it. All right, so we see the water potential is equal to the pressure potential plus the solute potential. So in other words, our water potential is equal to the pressure, which we said is +2 bars, plus the solute potential, which is going in the opposite direction, -3 bars. What that means is the overall potential is -1 bar, that the water will still be moving inside because of that solute. So we have a -1 bar of water potential. Okay, in this case, this was a pretty easy problem because we gave you the solute potential and the pressure potential directly. You just had to add them up. What if you had to calculate the solute potential first? Well, we have another formula for that, and that's where we're going to end today. The solute potential has the formula -ICRT. And what that means is the solute potential can be calculated by taking the negative of the ionization constant. So if you think about molecules that have ionic bonds and they ionize, right? So this is a constant depending on what solution you're in. Salt, right, actually will go into 2 particles, so that gets a 2 in water, right? Glucose and sucrose will keep its shape, so it will stay as 1 particle. So it has a 1 for the ionization constant. Most of the time, these are the only 3 we'd ever talk about: glucose, sucrose, and salt. So those are the ionization constants for it. C is the molar concentration. R is a constant, and this will stay the same every time. And T is the temperature, but it's got to be in Kelvin. So if you're given a temperature in Celsius, you've got to first convert it to Kelvin. All right, so let's talk about calculating solute potential. So let's say here, it looks like we got some sucrose, semi-permeable membrane here, lots of water over here. Well, it's pretty easy to see. Water will move from a high concentration of water to a lower concentration of water. So obviously, you can see the water is going to move across the membrane over there. So in other words, this solute, in this case the sucrose, is creating a potential for the water to move across. Let's calculate what that is. Here's your practice problem. A cell is sitting in a 0.5 molar sucrose solution. There it is. The temperature of the solution is 20 degrees Celsius. Okay, we've got the temperature. Calculate the solute potential. Okay, so I think we've got everything to do this now, right? So the solute potential is negative ICRT. Solute potential is negative, oh, what do we put there? Actually, I'm going to let you pause the video, see if you can work through the rest of this for a moment. Go ahead and pause me. Okay, did you get this figured out? Let's walk through it. So the solute potential is negative I, and we're talking about sucrose. So sucrose only goes to 1 molecule in water, so therefore that's a 1, so we got a negative 1 there. C is the molar concentration. Oh, they gave it to us, 0.5. So we got a 0.5 there. And you should be, of course, putting your units, right? 5 moles and all that stuff. Then we're going to multiply that times R, the pressure constant, 0.0831 liter bars per moles of Kelvin. I should have written that out, moles there. And then we're going to multiply that by T, the temperature, 273 plus 20 degrees Celsius. Because we were given Celsius, it has to be in Kelvin. So we're going to add that and make that 293 Kelvin. Okay, so obviously the kelvins are going to cancel. The moles are going to cancel. And so basically what we're going to be left with is if we multiply all those across, so just use your handy-dandy calculator and enter all of that in there. Looks like we get a solute potential of 12.15, meaning that this solute is creating a potential for the water to move of 12.15. Okay? So when you're calculating these problems, everything probably should be given to you. Just take a moment, look at everything, and it's as simple as putting some numbers generally into equation. Now, you might see an example where they ask you, or someone asks you to have the overall water potential, and so just remember that is just the solute potential plus the pressure potential. So once you've calculated the solute potential, you might then need to add the pressure potential to get the overall water potential. Okay, so in this video we looked at osmosis, the movement of water across semi-permeable membranes from high to low concentration, and we also, hopefully now you should be able to calculate some solute potential and water potential as things move across a membrane.